we have Tom McCoy, assistant professor of linguistics here at Yale.
Hey everyone, thanks so much for coming. So the big picture question motivating this talk is how can we build AI systems that learn as rapidly as humans do? So the side of efficiency I'm focusing on here is data efficiency. And Ilker already gave a motivation for this with the example of self-driving cars, but since I'm coming from the linguistics department, I'm obligated to also give the example from language. So this plot shows the number of words that an LLM, GPT-3, was trained on compared to the number of words that a human child encounters during development. And you might think that I made a mistake and forgot to draw the bar for the human child, but there's no mistake. There's just such an enormous disparity that the child does not even register as a single pixel on this plot. And this is GPT-3, which is a few generations ago. Current LLMs are more in the order of 1 trillion words of training data. So there's clearly some really, really big gap where it would be wonderful if we could bridge this gap somewhat. And the basic proposal I'll be developing in this talk is to lessen this gap by distilling Bayesian priors into neural networks. So overall, I'll first motivate this distillation approach and illustrate it with a case study in language. And then I'll extend it to some other case studies in concept learning and vision. And then I'll ask, after we show that this distillation approach is able to enable neural networks to learn more rapidly, I'll present some results analyzing these rapid learning neural networks to investigate what is it that's going on internally that enables them to learn rapidly. And then at the end, I'll zoom out just to reflect a bit more speculatively about the question of which avenues should we be pursuing or which questions should we be asking if we want to get neural networks to learn rapidly. So first, this approach I'll be proposing is really about 2 different frameworks in computational cognitive science, Bayesian models and neural networks. And so this is the way that people often think about the complementary strengths and weaknesses of these 2 approaches. One of the fantastic strengths of Bayesian models is that they're very rapid learners. They're probably the best models we have for modeling the rapidity of human learning. But they're often framed as being intractable or in naturalistic settings, that is, to get a Bayesian model that is expressive enough to deal with naturalistic data, this often becomes intractable to run inference over. And then in a complementary fashion, neural networks are very flexible and expressive. As we see with systems like LLMs, they can handle a very, very broad range of inputs, but they're also very slow learners, as the plot earlier just showed. And so the key question here is, how can we get a system that learns both rapidly and flexibly, combining these complementary strengths? And in fact, one of the earlier talks today, Alex Lev's talk, shows that one way we might be able to solve this problem is perhaps recognizing that Bayesian models might not be as intractable as they're often framed as being. But in this talk, I'll be pushing back on the other side of this equation by arguing that maybe neural networks are not as inherently slow at learning as they're often viewed as being. This proposal that I'll be working toward is called inductive bias distillation. It involves distilling a Bayesian model's inductive biases or its priors into a neural network. The basic motivation here is that hopefully the resulting system should then have the flexibility that is one of the great strengths of neural networks, as well as the strong inductive biases or the strong priors that enable the Bayesian model to learn rapidly. So this sounds very nice, but how can we actually do it? We developed this approach in this paper with Tom Griffiths. So I'll first give the high-level overview of it. It has 3 basic pieces, and then I'll walk through each of these pieces in more detail with a specific case study. So the first step is we want to start by defining some inductive bias or some prior that we want our learner to have, and we define this inductive bias via a probabilistic model that is the prior component of the Bayesian model. And in the case study based on language, what this probabilistic model defines is a probability distribution over possible languages. And then the second step is we will sample a whole bunch of languages, synthetic languages, from this probability distribution over languages, such that we can use all of these sampled languages as training data for a neural network. And then the final step is to have a neural network learn from all of these languages that we have sampled using a special type of learning called meta-learning. The basic intuition of meta-learning is that the learner is exposed to many different languages, and through this exposure, it's able to figure out what commonalities cut across all the languages, and also what are the controlled ways in which languages can vary from each other. And then this information will enable it to learn new languages more rapidly. So let me now walk through each of these steps in more detail. The first step is we need to define some probabilistic model that gives us a probability distribution over languages. And for this case study, we'll be starting with formal languages, where a formal language is a set of strings defined by some abstract rule. So an example of such a rule would be plus of concatenate of AB, where concatenate of AB gives you the string AB, and then plus is the Kleene plus operator, which tells you you can have one or more copies of its argument. So overall, this formal language gives you a set of strings, each of which is one or more copies of AB, such as the string AB, the string ABAB, the string ABABAB, etc. So these formal languages are definitely very abstract and kind of idealized, but the reason we're talking about them is they are inspired by the structure of natural language. For example, the formal language I just showed you that has this alternating ABABAB structure is reminiscent of something you can see in natural language when you have nested prepositional phrases. So if we suppose that A stands for a preposition and B stands for a noun phrase, then the ABAB structure arises in something like over the river, through the woods, to grandmother's house. And so the way we set up a probabilistic model in this domain of formal languages, which is inspired by some work by Yang and Piantadosi, is we start by defining a set of primitives, like the vocabulary items A and B, and then the connectives like plus and or, and then have a simple probabilistic model that can probabilistically combine these primitives into rules like plus of or of AB. So that's our probabilistic model, which gives us a distribution over possible formal languages. The next step is to sample a whole bunch of formal languages from this distribution. This is the most straightforward step because this probabilistic model that we have is a generative model. It's essentially a context-free grammar, or you could call it a metagrammar because we sample grammars from the metagrammar. And so each bullet point here would be a different formal language rule or a formal language grammar that we might sample from this metagrammar. So we just sampled a whole bunch of them, and now we have this whole set of sampled languages. And the final step, which we'll spend the most time on, is having a neural network meta-learn over all these formal languages that we sampled. So first, let me give the high-level intuition about meta-learning. The very first board game you ever learned how to play probably took you a while to learn, but after you've learned 50 different board games, now you can probably learn your 51st much more easily. Because by this point, you've learned a lot about how board games work, you've learned what it means to roll some dice and move that number of positions, you've learned what it means to draw a card and carry out an action, and all of this knowledge that you have essentially gives you inductive biases that enable you to learn new board games more easily. So this is an example of meta-learning, also called learning to learn. You've learned how to learn new board games more easily. What we are doing here is essentially the same intuition, but with formal languages rather than board games. So what we do is we show a neural network many different formal languages, all the ones that we've sampled from our probabilistic model, which should give it linguistic inductive biases, in other words, priors about which types of languages are likely or unlikely. And by controlling the languages that we show to the network, we can control the model's inductive biases. So specifically, if we sample the languages from the prior of some Bayesian model, this should then give the neural network the same priors as that Bayesian model had. For those who are familiar with the idea of universal grammar, one intuition is that this is kind of like giving universal grammar to a neural network, although here I'm using the phrase universal grammar very generally to essentially mean whatever inductive biases guide language learning without it necessarily needing to be as specific as the types of priors that are often associated with the term universal grammar. Now, I want to note that this procedure is not a hypothesis we're making about what humans are doing in language acquisition, because what this would mean is that the way you acquire your first language is by previously having acquired 20,000 other languages, which is not a very plausible account. So in this work, we are just using meta-learning as a useful computational tool that allows us to manipulate the inductive biases of a neural network. I will say so that there are some close connections between meta-learning and evolution. Dan Grimmer has a lot of thoughts on this. So in a bit more detail, meta-learning has kind of this inner optimization, such as learning a single language that's akin to one individual's lifetime, and then it has an outer optimization of many episodes of learning an individual language that are kind of like successor generations in evolution. And so there may be domains where it really does make sense to actually lean into this evolution analogy and treat it as a proposal for where human inductive biases came from. We're not making the argument here, but it's one I'm happy to talk more about. The result of this meta-training process is something that we call a prior trained neural network, because the network has been trained to have a particular prior. And so now let me show some results of how this works. Before I show the actual results, let me say how this plot is structured. The horizontal axis shows, or what we're doing is we are seeing how quickly different types of models can learn formal languages. And so the x-axis shows different numbers of training examples. For example, we see how well models can do with just one example, or with 10 examples, or 10,000 examples. It's on a logarithmic scale. And then the y-axis shows the F-score, which is a metric of how well you've learned the language, ranges from 0 to 1, and it's averaged across 56 different formal languages that we evaluated these models on learning. So first, this line shows how well a probabilistic model does at learning these formal languages. This is a Bayesian model from Yale and Piantadosi, and as we would expect from the Bayesian model, it can learn them very rapidly. After just 10 examples, it's getting a very solid F-score of 0.75, and after just 100 examples, it's doing very, very well at even some pretty complicated formal languages. And then this line shows a standard neural network, and as we would expect from standard neural networks, it learns much more slowly, needing something like 10 times as much data as the Bayesian model to learn the same formal languages. But now this line shows a prior trained neural network, a neural network that went through meta-learning. And now, despite being a neural network, its learning behavior looks much more like the Bayesian model. And one thing to highlight, which I guess I didn't mention yet, is that the standard neural network and the prior trained neural network are exactly the same architecture as each other. In this case, they're both just plain old LSTMs. You can do the same thing with plain old transformers. The only thing that differs and the only thing that meta-learning gives you is a new starting point. So typically with neural networks, you initialize them with just randomly chosen parameter values. What meta-learning does is it finds a very targeted starting point, and that seems to be enough to give this qualitatively different learning behavior. Now, the results in the previous slide were with these very abstract formal languages, but it's natural to wonder whether these distilled inductive biases also provide learning benefits for natural language. So to test this, we took those same meta-trained networks that had been meta-trained on these formal languages, and then checked what happens if we then further train them on an 8 million word data set of English. And so as a first pass of evaluating these systems, this plot shows perplexity, where lower is better. And if we compare the standard neural network to the prior trained neural network, each dot here shows one rerun of the model, and you'll see that pretty reliably the prior trained one gets a better, that is lower perplexity than the standard one. So it is statistically significant, but note that the effect size is very tiny. It's a difference of around 19.67 up to 19.75. So a significant but not very large difference. With that said, however, perplexity is a very generic broad metric that averages over an entire corpus. And so we might not expect to see very clear benefits within this very broad metric, but we might see learning advantages emerge more clearly if we did a more targeted evaluation. So as an example of a more targeted evaluation, we consider recursion in language, where in this inductive bias that we have distilled into the neural network, one of the primitives that defines this prior via the probabilistic model that we use to define the prior, one of the primitives is the Kleene plus primitive, which is essentially a primitive for recursion, because it allows you to have one or more copies of some unit. So for example, plus of B would give you B, or BB, or BBB, essentially a form of recursion. And so this makes it natural to ask whether having this recursion primitive improves the handling of recursion in natural language for systems that have been meta-trained on data based around this recursion primitive. So here's how we get at this. Consider these two sentences. The book sitting on the table is blue, and the book sits on the table is blue. Well, if you want to test whether a system has captured the syntactic structure of English, you could check whether that system recognizes that sentence 1 is better than sentence 2. Now, how does this relate to recursion? Notice that these two sentences have a prepositional phrase in them on the table. Well, we can apply some recursion to that prepositional phrase and just add another prepositional phrase next to it to get the book sitting on the table in the kitchen is blue versus the book sits on the table in the kitchen is blue. And even though we've added this extra prepositional phrase, it's still the case that 1 is better than 2. And indeed, we could add as many prepositional phrases as we wanted in that slot, and you should still be able to get the same judgment that 1 is better than 2. And so the evaluation we ran was looking at sentences like that with anywhere from 0 to 10 prepositional phrases added in that slot in the sentence. And then we checked at how accurate the different types of models were at telling which of those two sentences was a better formed sentence of English. And you'll see that both types of neural networks have performance that degrades noticeably as the levels of recursion increase. But there's quite a big gap where there's much less degradation in performance for the prior trained network than the standard network, which is evidence that the meta-learning process has imparted some benefits for handling syntactic recursion. And so this plot is showing one type of sentence template, but we ran similar analyses with a total of 12 different types of sentence templates. And in general, you will see that the red circles, that is the prior trained networks, are generalizing more robustly than the blue triangles, the standard neural networks. Okay, so that's the case study I'll spend the most time on using this inductive bias distillation approach to transfer the benefits of Bayesian models into a neural network for purposes of language learning. Now I'll briefly mention a couple other case studies of this approach in concept learning and vision. So first, this case study on concept learning was led by Ioana Marinescu, who's now a PhD student at NYU. And so here we're considering the task of logical concept learning, where a person or model is given some set of objects, each labeled with a binary label of yes or no, meaning either it does belong to the concept or it does not belong to the concept, and then they need to try to figure out what the rule is that defines the concept and then extend it to new objects. So in this case, the intended concept is green or triangle. You should say yes if the object is green or a triangle, but no otherwise. And there's this very nice paper by Noah Goodman et al. That introduced a Bayesian model called rational rules, which gives a fantastic fit to human behavior on performing this type of task. And what we did was we used inductive bias distillation to distill this rational rules model into a neural network classifier. And what we found, first, the red dots are showing a standard neural network where the x-axis gives human predictions on this task, the y-axis gives the neural network predictions, and the standard neural network in red just isn't doing anything because you only get 9 training examples in this particular task, and a standard neural network just can't really extract anything out of those 9 examples. But then the prior trained neural network, given those same 9 examples, now, just like the rational rules model, correlates very well with the human judgments. The other case study I'll briefly mention is about vision. So this one is led by Max Gupta. And this one is about the task of discerning the abstract relation of same versus different. So the way this is set up, the convolutional neural network is given an image containing 2 objects, and then it needs to classify whether the 2 objects are different from each other or the same as each other. So it seems like a really trivial task to us, but it turns out that for a basic convolutional network, it's actually very hard. So because this is a binary classification task, the chance accuracy would be 50%. And it turns out that across a whole bunch of different ways of instantiating this task, basic convolutional networks are getting right at chance 50% behavior. But then if we take the exact same architecture, but just modify the training procedure to go around meta-learning rather than standard learning, now they're doing fantastically, well over 95% on the same tasks. So it seems that meta-learning can also help you with learning abstract tasks in addition to getting the more rapid learning. Okay, so we've now seen several examples of how meta-learning or inductive bias distillation can enable neural networks to learn more rapidly. And I should mention that I was just absolutely astounded that you can get neural networks to do this. So for a little bit of background, I first learned about meta-learning when I was a PhD student. Tom Griffiths came to give a colloquium talk at my PhD department where I learned about meta-learning for the first time, and I thought, in principle, it seems like this could be something that could get neural networks to learn language rapidly. There's no way it could actually work, so let me just try it to confirm it doesn't work and then move on with the other language learning models I was working on. But then it just worked astoundingly well, so I had to really revise my beliefs about what neural networks are able to do. Because if you think about it, this task of learning formal languages, the formal languages are very compositional and symbolic and recursive. All of these are properties that seem very non-neural network-ish. And yet meta-learning is able to get neural networks to do this very non-neural network-ish thing of really rapidly learning something discrete and compositional. So this makes it natural to ask, how are they doing it? What is it about these meta-learned neural networks that makes them so different from more standard neural networks in terms of their learning ability? And one possibility is that what the meta-learned networks are doing is learning compositional structure in their space of parameters. And so we've investigated this hypothesis in some work led by Abi Tenenbaum, and I think this hypothesis is most clearly illustrated through an example. So we'll be going back to models that were meta-trained on formal languages, and specifically we'll focus on a type of formal language that we call A parity, B parity. So some examples of this type of formal language, one example would be Q odd Z even, where every string in the formal language has to consist of an odd number of Qs followed by an even number of Zs, such as QQQZZ or QZZ, etc. Or you might have Q odd Z odd, where now it has to be an odd number of Qs followed by an odd number of Zs, like QQQZZZ or QZZZ, etc. So more generally, any one of these formal languages is defined by these two elements A and B, and then the parity of each one, that is whether each one needs an odd or even number of occurrences. And so we have a neural network that it has meta-learned over a whole bunch of formal languages of this A parity, B parity type. And now once we have that as a starting point, we can then further train it on any one of these languages to get it to instantiate that language. So we might pick the formal language Q odd Z even, and then have the meta-learn model learn Q odd Z even. What this now gives us is a neural network that instantiates this formal language Q odd Z even. And the way we will think about these neural networks is we will think about the neural network as a vector of weights. Now, more typically, you think about the neural network weights as being a whole bunch of different matrices, but just for simplicity, we can take all the parameters out of those matrices and just string them together into one big vector that we can call theta, say. And so this gives us a vector of weights now that captures this formal language Q odd Z even. And we can do the same thing for a couple of other formal languages to get a vector of, so we take our meta-learned initialization, further train it on M even Z even. This gives us a vector of weights that instantiates M even Z even, and similarly for M even C odd. And so now we have vectors of weights for each of these three different formal languages. And what we can now do is we have these three vectors, we can do arithmetic over them, we can add them and subtract them because you can add and subtract vectors. So we take the vector of weights from the Q odd Z even network, subtract the vector of weights from the M even Z even network, and add the vector of weights from the M even C odd network. So this gives us some new vector of weights, which we can then plug into a neural network and see what the neural network does when it has those weights. And specifically, what we check is when this produces strings, are the strings consistent with the language Q odd C odd? So why Q odd C odd? Well, if you look at the math here, the assumption we're making is that the two Z even terms will cancel out since we have Z even minus Z even, and then the two M even terms will cancel out since we have minus M even plus M even, leaving us with Q odd C odd. And the short answer is it works, which I was really astounded at how well it works. It gets an F-score of 0.98, where the highest possible you can get is 1, which shows that these meta-learned neural networks have realized some sort of compositional structure in the parameter space of the neural networks, such that you can add and subtract entire neural networks in meaningful ways. So these analogies reveal that there is compositional structure in the space of weights induced by the meta-trained neural networks, which shows us that optimizing for rapid learning produces compositional analogy structure. So this actually gets at the question Julian started the last discussion section with, which was traditionally cognitive science has been optimizing our models for compositionality and then saying hopefully efficiency will come out sometime in the future, but what if we instead optimized for efficiency? What would our models look like? Well, a really interesting outcome of this work is you can think of meta-learning as explicitly optimizing for rapid learning, that is optimizing for data efficiency within some specific domain of functions. And it seems that if you optimize for data efficiency, algorithmic compositionality falls out naturally. And so perhaps by optimizing our models for compositionality, we've also been optimizing them for efficiency all along as well. And so this, I think, is evidence that if we want systems that can learn rapidly, systematic compositional structure in their algorithmic space might be very important. Because these neural networks did not have any constraints imposed on them to realize this type of compositionality. They had they're able to do anything they want to satisfy these pressures for rapid learning. And out of the entire universe of possible things they could be doing, the thing that they selected was this approach that involves systematic analogical structure, which suggests that there is something very natural about compositional algorithmic components that can be recombined that might be really important for rapid learning. Okay, so then a high-level takeaway from all these results is that Bayesian models and neural networks are not at odds with each other. So historically, in the history of the field, they often have been pitted against each other. Like in 2010, TICS had these dueling papers between the Bayesian camp and the neural network camp. But what we've shown here is that it is possible for a single system to be a Bayesian model at an abstract level, something like Mars computational level, but then a neural network at the algorithmic and implementational level. Okay. In the last few minutes, what I'm now going to do is just zoom out and talk at a higher level about what sorts of questions we might want to be asking if we want to enable neural networks to learn rapidly. So the first question is just, why do we want neural networks to learn rapidly? Because definitely we might instead want to pursue other types of models that might be able to learn rapidly more naturally. Well, I think there's both an AI motivation and a cog-sci motivation. The AI motivation is just empirically, it does seem likely that neural networks are here to stay as the heart of modern AI, and so if that continues to be true, we definitely want to figure out ways to make them learn more rapidly. And then the cog-sci motivation is, it's clear that the human mind can learn very rapidly, and it's also clear that whatever the human mind is doing must be happening inside the brain, which is some sort of neural network, one that is very different in many ways from artificial neural networks, but still a type of neural network. And so if we want to fully understand the mind, we will need some story for how rapid learning can be realized in neural network tissue. And so a first type of contrast that I think is useful to think about for this question of enabling neural networks to learn more quickly or giving them more helpful inductive biases is two possible routes to giving useful inductive biases to neural networks, namely via architecture or via data. So first, on the side of architecture, I think, in fact, the way that is most common for reasoning about inductive biases in neural networks is via their architecture. In fact, in the ML community, people often use inductive bias as essentially a synonym for the architecture. And this is definitely one thing you can manipulate to modify the inductive biases of neural networks. So, for example, Bob and I and Tal Linzen have some work showing that for learning syntax, standard neural networks have a linear structure, but you can get faster learning and better generalization if you instead switch to an architecture that builds in tree structure, reflecting the tree structure of natural language. But then the work I talked about today, this inductive bias distillation work, instead holds the architecture constant and manipulates the data, specifically giving some very specialized training data, sampled from a probabilistic model, and then optimized over using this specialized meta-learning procedure. And I do think there are there is potentially interesting work to be done about the strengths and weaknesses of each of these routes toward inductive biases, and they might have complementary strengths. Another higher level point that connects to several of the other talks today is, I think there is this very intuitive idea that we should try to combine the complementary strengths of neural networks and structured Bayesian models. Each one of them seems to really get something right, and what they get right seems to be complementary in a way that would be wonderful to combine. But the question is, how should we do it? Well, I'll contrast two different approaches. One you could call neural networks plus Bayes, and the other would be neural networks equal Bayes. So the neural network plus Bayes would be exemplified by what Tyler talked about this morning, the model synthesis architectures, something like you use a neural network to generate structured Bayesian models, and then run inference over those models. So your overall system has some Bayesian components and some neural network components. In contrast, the neural networks equals Bayes approach is something like inductive bias distillation, what I just talked about, where now we have a single system that is both of these things simultaneously. That is, create a neural network that realizes a Bayesian model by distilling the Bayesian model into the neural network. And I think it's unclear which of these approaches is better. I think they both have things to recommend them, but also some shortcomings. So another thing where I think they're both exciting, and I think it would be good to be exploring both of them. So first, one definite benefit of the neural networks plus Bayes approach is that it's more interpretable. What it gives you is some symbolic model that a human can look at and reason about, whereas the inductive bias distillation, what it gives you is just some set of neural network initial weights where Abhi's made progress on understanding that, but we still don't have a good understanding of what's going on there. Another benefit of the neural networks plus Bayes side of things is that I think it's likely to be more robust. So specifically, this is coming back to a plot that I showed you earlier, where we saw that this was the evaluation of recursion, where a prior trained neural network generalizes much more robustly than a standard neural network, but it still does show some pretty substantial degradation in performance. Whereas if we had instead synthesized some symbolic grammar, then it would start off with 100% performance, and then it would continue to have 100% performance because of the guarantees that you get with symbolic models. And there are very clear arguments why you would want that sort of robustness. On the flip side, for reasons why we might want a single system that is simultaneously neural network and Bayesian, a first reason is that this is definitely important for cognitive science, for the reason I already mentioned, since we have good reason to believe that the mind is Bayesian in at least a lot of settings, but also good reason to believe that it is implemented in the brain, and so we should have some theories about how those things can both be true of the mind. The other more speculative reason that has me excited about this direction is that there might be some types of flexibility that you get out of realizing your Bayesian model in neural tissue rather than symbolic tissue. And for this, I'll give an example from this paper with Aaron Grant, Paul Swensky, Tom Griffiths, and Tomlinson. So I won't go into detail about the task here, but what these networks were doing was they had to learn some phonological rules. And the way this was set up is there was a space of types of rules that were allowed and that the models encountered during meta-learning, but then other rules that also are reasonable, but that just are impossible in this framing. So for example, the possible rules include things like you can insert a consonant at the start of a syllable, but something that's impossible is there's never a rule where you insert a consonant at the end of a syllable, because it turns out there is this asymmetry in the languages of the world. And when we have a network meta-learn over many of these possible rules, we see that it is able to learn possible rules much more quickly than a randomly initialized network. So it needs something like 150 examples after meta-learning compared to 20,000 examples before meta-learning. Okay, so that's similar to the results I've shown you already. But then the other thing that's interesting is even though the model has never seen any of these impossible rules, it also gets an enormous efficiency boost for the impossible rules, these unintended types of rules that it has never seen anything like. And just to zoom in, this does show you that it has a much harder time with the impossible rules. I should have mentioned the y-axis is how many examples it needs to learn the rule. So it does need a lot more examples to learn an impossible rule than a possible rule, but it still does learn it, and it learns it much more quickly than it would have when it was randomly initialized. So in some sense, this is a clear failure of what we wanted, since our goal was to distill this Bayesian model into the neural network. Well, the actual Bayesian model would be literally incapable of learning these rules because it can't even represent them, let alone learn them. And so the fact that these networks can eventually learn them is evidence that they do not perfectly realize the Bayesian model. But there's also an argument that this might be a feature rather than a bug, because it shows that the meta-learn system does have the flexibility that it is able to learn other reasonable things that share some commonalities with the types of things it has seen before, a type of generalization that you would not get if you were fully constrained by the language of the rules that we were using in the symbolic probabilistic model. So I think it's potentially the case that using a neural network as the implementation of your Bayesian model might give you a way to benefit from your priors without being constrained by them. But this definitely remains very speculative. So just to wrap up, we've shown that Bayesian inference can be realized in standard neural network architectures, enabling them to learn rapidly in stark contrast to what we often think of neural networks. We've also shown that this rapid learning in neural networks may depend on systematic compositional structure in the parameters, given that it seems that such structure naturally arises when we optimize for rapid learning. One open question is, what is the best way to combine the complementary strengths of Bayesian models and neural networks? I presented one sort of approach for doing this. Tyler's presented another. There might be also syntheses of these, and I'm definitely excited to see how this space develops. With that, I'd like to thank all my fantastic collaborators, and thank you all for listening.